Okay, welcome guys to Physics 390 class 18. This class is on non-degenerate perturbation theory, and it comes from chapter 7.1 of our textbook. This is going to be about trying to understand new Hamiltonians, that is, new physical systems in terms of systems that we already understand, but which the new systems just differ a little bit from the old system or the system we understand. So we can use what's called perturbation theory to get an idea of what happens in the new situation. So let's see how it works. Okay, so the usefulness and the setup of perturbation theory. Okay, so suppose we have a new Hamiltonian H for the PHYS, and it's close to a previous Hamiltonian H0, which we've already solved. So it turns out we can get a good approximation to the new solutions using previous solutions, as long as our new Hamiltonian is pretty close to the Hamiltonian which we've already solved. And that's the usefulness of what's called perturbation theory. So as an example, here's the infinite square well, which we're familiar with. And suppose we have just a little bit different potential with a little bump here. Then that's pretty close to the Hamiltonian of the infinite square well, which is 0 all the way across here. Just this tiny little bump is just a small difference. So we can get a good approximation to the solutions of the system with the small bump using our previous solutions and some expressions which come out of the setup of perturbation theory. So let's look at the setup. So to set this up, we're going to use a parameter lambda. And that parameter will let us organize the corrections that are involved in the approximation of the new solution. Okay, so lambda is an organizing parameter to keep different, what we call orders of corrections to the previous solutions organized and sorted. So we start by writing the new Hamiltonian H in terms of our old Hamiltonian plus this parameter lambda times h prime, where h prime we call the perturbation. And we start with lambda, imagining lambda to be a small parameter, but eventually we'll let lambda equal 1 to get the full new Hamiltonian, h0, our original previous Hamiltonian, plus the perturbation, h prime. So eventually we'll dial up lambda to the full value of 1, and our Hamiltonian will then be our full new Hamiltonian, and our approximation will be the full approximation. Okay, so with this lambda small parameter, we express the energies and the wave functions as a power series in lambda. Okay, so we take the new wave function psi n as psi n0, the previous wave functions, plus first power of lambda times a first order correction, plus second power of lambda times a second order correction, psi n1 for the first order correction, psi n2 for the second, and similar for the energies. So again, these are the new solutions, psi n and en, for the new Hamiltonian, which we're interested in. These are the previous solutions, which we already have for the Hamiltonian H0. These are the first order corrections because they're grouped to lambda to the first power. So the first order corrections to the wave function here and the energy here. And these would be the second order corrections. So psi n2, it's not psi n squared. This means psi n2 for second order. And this is en2 for second order correction to the energies. Okay. So we express the energies of the wave functions as power series in lambda. Okay, so why would we do that? Well, we're going to eventually write the PHYS for our new system in terms of these expansions in lambda, and then group like powers of lambda and get a series of expressions which enable us to get the first order and second order corrections. So let's see how that works. So using the power series in lambda to find the corrections. So we express the new problem, which is H psi n equal En psi n. So this is the new Hamiltonian, the new wave functions, the new energies, the new wave function again. This is the TISC using the power series. So we have H is H0 plus lambda H prime. That's the original Hamiltonian plus lambda times the perturbation H prime. Psi n is the original wave function psi n0 plus the corrections lambda times the first order correction plus lambda squared times the second order correction. And then En here on this side becomes En0, the first order, sorry, the original energy plus the lambda times the first order correction, En1, plus lambda squared times the second order correction, En2, etc. And then here again, we have psi n as the original solution plus the first and second order corrections. Okay, so that says just substituting in these these expressions in terms of lambda for each of these, whether they be the H is the original Hamiltonian plus the perturbation or the power series expansion for the wave function and for the energies here. So, okay, what do we do then? Well, we multiply this out and we group like powers of lambda, okay, to organize the corrections. Okay, so we're going to multiply this out and we're going to get something like this. So on this side, let's look at just a couple terms. We won't do every term, but we'll look at a couple terms. So the first term we get is H0 psi n0, which is over here. The second term we get would be lambda H0 psi n1 with a lambda in it. The third term would be lambda H prime psi n0. So those are both first order in lambda. They're multiplied by the first power of lambda. Then for lambda squared, we get lambda squared H0 psi n squared, psi n2 rather, not psi n squared, but psi n2 plus H prime, sorry, lambda squared times H prime psi n1. And on this side, we get En, the first term we get is En0 psi n0, and so on and so forth. We can multiply out these and find like powers of lambda over on this side as well. Okay, so if this is going to be true, then each, since lambda is a parameter which can vary, it's a small parameter, so it can vary. It's a power series here. Each order of the coefficients of each order of lambda must match on each side. So for the constant term, that is the lambda to the 0th power, so just the constant term is our previous solution. So that's H0 psi n0 equal En0 psi n0, which is right here. So that's our previous problem, the so-called original, previous, or unperturbed Hamiltonian with the original solutions and the original energies. So the constant term just gives back what we already know. The first order term, lambda to the first, is we would take, gives this H0 psi n1 plus H prime psi n0 is equal to what's multiplying lambda on this side, En0 psi n1 plus En1 psi n0. Okay, so we get this expression here, which has both the first order, it has the Hamiltonian, the original Hamiltonian, the perturbation. It has the original wave function, the correction to the wave function. It has the original energy and the correction to the energy to first order. So it has a lot of stuff in it. So we have to do a little bit of work here, but it can, this can be used if we see that by nice manipulations to find the first order corrections for the energies and wave functions. Namely, for the energies, that would be En1. Remember, En1 is the first order correction to the energy, and psi n1 would be the first order correction to the wave function. Okay, and so please see the text for this. There's the energy derivation is not too long, but the one for the wave function takes a few steps, and I'm going to just give you the results here. So the first order correction to the energies is just the expectation value of the perturbation H prime in the unperturbed state N. So again, for the nth energy level, the first order correction En1 is the expectation value of the perturbation in the nth previous or unperturbed wave function. Okay, so that's a nice result. It's a mouthful to say, but it's pretty. It's about as simple as you could hope. Again, to get the first order correction to the energy, you take the perturbation and you take the expectation value of that in the that state's unperturbed wave function. Okay, the expression for the first order correction to the to the wave function psi n1 is a little bit more complicated. It's a sum for m not equal to n of the not exactly an expectation value, but really a matrix element of psi m0, the perturbation psi n0. So it's like an expectation value, but we have m not equal to n. So it has the same form, but it's not an expectation value at any particular state. It's really an overlap integral. So that over the difference in energies between n and m, which since n is not equal to m, we're not going to get 0 here. Now there is a complication here, which is if there are two states n not equal to m which share the same energy, we're going to be dividing by 0. And that's why this is called non-degenerate perturbation theory, because we assume that if n is not equal to m, then En is not equal to Em, and we're not dividing by 0. In the case that we get for n not equal to m, we get En0 minus Em0, 0. That's called degenerate perturbation theory, and we'll look at that in the future. But anyway, let's not worry about that right now. Let's assume it's non-degenerate, so we're not dividing by 0 here. So this is our expression for the first order corrections for the wave functions. Okay, so it's a sum over this matrix element over the difference in energies weighted by the for each m for each m that's being summed here, we multiply that ratio by the unperturbed wave function psi m0. Okay, so the second order term gives, so we look at the coefficients of lambda squared here. That gives h0 psi n2 plus h prime psi n1 is equal to en0 psi n2 plus en1 psi n1 plus en2 psi n0. Okay, so again, a bit of a mouthful, but using the results of the first order energies and some manipulation, we can find the second order energy corrections. Again, see the text for the derivation if you're interested. But they are the second order corrections to the energies for En2, similar to the informed to the first order corrections to the wave functions, in that we have a sum for m not equal to n. But notice a couple of differences. So first, the matrix element on the top is squared, so that this top would have dimensions of energy squared over the denominator, which has dimensions of energy. So we get a dimension of energy, which is what we want for this En2 here, because it's an energy correction. Also, we don't have the psi m0 out here because it's not a wave function correction, so we don't have that psi m0. But otherwise, they look kind of similar. So that's the second order corrections. And that's pretty much as far as we go. It is possible to write the second order corrections to the wave function, so psi n2, but it's quite complicated and usually doesn't add much to the accuracy of the approximation. So generally, we'll go to the first order corrections to the energies, see what they are, the first order corrections to the wave functions, and then possibly the second order corrections to the energies. And that's generally as far as we'll go. Okay, so we have those expressions. Let's look at an example, one that's near and dear to our hearts, hopefully, the ISW, or the infinite square well. So remember, the infinite square well has solutions. Psi n0 of x is square root of 2 over a sine of n pi x over a. Okay, so that's those are harmonic solutions inside the well that go to 0 at both sides of the well of width a and normalized by square root of 2 over a. So suppose we perturb that, and we perturb it just by letting our perturbation h prime equal to v0. So it doesn't depend on x. It's just a constant. So here's a picture of that. Our square well went all the way down to 0. Now we've added a constant v0. So the base of the square well has been raised by an amount v0. Okay, so within the well, the potential energy is no longer 0, it's v0. It's still going to be no forces because it's a constant potential. So a classical particle would not experience any forces here. So it's still a flat potential, but it has a value of v0 because it's been raised up. Okay, so what are our expressions for the perturbation theory tell us in this case? Okay, so the first one, just to remind you, is that the first order correction to the energy is the expectation value of the perturbation in the unperturbed wave function n. So let's see how that applies here. So we have en1 is psi n0. Our h prime here is v0, which is a constant. So therefore, since it's a constant, we can pull it out of this expectation value, and we just get v0 times the inner product of psi n0, psi n0. But since psi n0 is normalized, this would be 1. Psi n0 would be 1 by normalization. So this just becomes v0. So en1 is just v0. So the first order corrections to the energies are just v0, the amount that we've the energy of the perturbation. Okay. The second expression is for the first order correction to the wave function, psi n1, n for the nth wave function, 1 for the first order correction, which is this sum here. So here, putting in this sum, we substitute for h prime v0 again. And then since v0 is a constant, so here's our expression, sum for m not equal to n of psi m0 v0 psi n over the difference in energies times psi m0. So it matches what we had before, except we have v0 for h prime. So v0 is a constant, so we can pull it out of this, effectively this, with this a prescription for an integral, and we get psi m0 psi n0. Okay, but for the infinite square well, if m is not equal to n, these are orthogonal. Psi m0 is orthogonal to psi n0. So this is going to be 0 for all m not equal to n. So we get a 0 here in the numerator, and so this is just 0. So there's no correction to the wave function. So psi n1 is 0. So to first order, there's no correction to the wave function. Okay, and our second expression for the second order energy corrections is the sum for m not equal to n of this matrix element squared over the difference in energies. So if we look at that, we get a similar argument. Here's the just taking this formula, replacing H prime by V0, and we get the matrix element with V0 of between M and N, quantity squared, but we can pull that out of the matrix element, and then of course it's squared. So we get the inner product between psi M0 and psi N0 squared times V0 squared. But just like before for the wave function, since these for M not equal to N, these two are orthogonal, psi M0 and psi N0 are orthogonal, this would be 0. So even when we square it, it's 0. So we get 0 for the second order correction to the energies. Okay, so in conclusion, each energy level, En0 of the infinite square well, remember those go up as n squared. We don't have the formula on here, but they go up as n squared. It's h bar squared, pi squared, n squared over 2m a squared, if you're counting. I think I got that right, but anyway, En0 goes as n squared, but each one of them is raised by an amount equal to V0. So what we've done is basically just raise all by lifting the floor. We've added a V0 to all of our energies, which kind of makes sense. We've just added a constant potential energy, which each, and before we just had kinetic energy because there was no potential energy before. So we've just added a constant potential energy to all of the energies. So all of them are raised by the same amount. And there are no corrections to the wave function solutions psi n0x for this perturbation, because we found psi n1 was 0 because of this sum and this orthogonality here. Okay, so this is an example of an application of perturbing with a perturbation. It's a constant perturbation. So we just get a constant energy to the first order, 0 to the second order, 0 correction to the wave functions. That's usually, we almost always get a, well, we always get a first order correction of the energies. In general, if it's not a constant, if it has any kind of x dependence, we're going to get a non-zero correction to the wave functions. So this is kind of a special case, but we used it here just to get the feeling for these, hopefully start to get a feeling for these expressions here. Okay, so just to sum up, we have non-degenerate perturbation theory. So we're assuming that all the energies are not equal to each other. So we can do these sums here. When m is not equal to n, we don't divide by 0. That's what the non-degenerate means. We take a known system, like the infinite square well, we change it a little bit. Either we lift it here, or like on the earlier, we put a little bump in it. So we change it a little bit. And we express the solution to the changed or perturbed system in terms of the solutions to the original or unperturbed system. And we're able to get a good approximation to what happens in terms of what we already know. It's not always exact. Here it is, turns out to be exact in this example on this slide. But it's not always exact, but it gives us often enough accuracy that we can get a grip and an understanding of what happens in the perturbed system. Okay, so that's that's non-degenerate perturbation theory. Okay, thanks for listening, and I will see you in class.